G'day guys, Luke from Mets here. I want to talk about why having a longer lever results in higher velocity at the end of that lever. So a couple of things we need to go through first. Let's talk about angular momentum. We know that equals moment of inertia multiplied by angular velocity. We also know that these two are inversely proportionate. So when moment of inertia increases, our angular velocity decreases and vice versa. Moment of inertia means the distance of the mass from the axis. So the further the resistance is, or the further the mass is from the axis, the lower our angular velocity. So let's go through two situations. Situation number one is that we're going to choke the grip. Okay, when we choke the grip, the axis is going to be our wrists, which will be attached to our force, basically here. So force and axis are really close together, okay? The resistance will be the center of mass of the cricket bat, which let's just say it'll be about there, okay? So by choking the grip, we keep the force arm the same, but the resistance arm is now closer to the axis. If in green, I put where we maybe normally would hold the bat would be up here, the axis and the force is still the wrists and the hands, but the resistance is still down here, but you can see the resistance is a lot further away. So in the green, our moment of inertia is higher and our angular velocity will be lower. Now this is where people get confused. In the context of VCE PE, we don't need to know this equation, but it really helps in explaining why having a longer lever is better for velocity. So linear momentum, which again, you don't need to know this, but I'm demonstrating it. Linear momentum equals angular velocity multiplied by the radius of the lever. Sorry, I've made a mistake. Linear velocity, my mistake, equals angular velocity multiplied by the radius of the lever. So when we're talking about linear velocity, we're talking about how far the end of the stick is moving, the end of the bat, okay? So let's go through the scenario. Scenario number one, in the black, we've choked the grip, so we're looking at this one here. We've actually reduced the moment of inertia because now the resistance is closer to the axis. And that's actually going to increase our angular velocity. Okay, so what that means is we can actually swing the bat faster. We can swing the bat faster, but we can't move it as far. The linear velocity is actually lower. So if we were to move our wrist through its full range of motion, maybe the bat's going to move that far either way. That would be our linear distance. So let's make up some numbers. Let's say that our angular velocity in this situation is 10. I'm just making up a number. And our radius of the lever, so this distance here, is, let's say it's 8. 8, that's the radius. Which means our linear velocity is going to be 80. Because 10 times by 8 is 80. That's our linear velocity. That's how fast the end of the stick is moving, the end of the bat. All right, situation number two. In the green, we have a higher moment of inertia because this distance is significantly longer. Therefore, we're going to have a lower angular velocity. So maybe our angular velocity here is, let's say it's 8, because our angular velocity is now lower. But what's happened is our radius of the lever is now longer. So instead of 8, maybe now it's 12. So that makes our linear velocity, 8 times 12, at 96. So we've actually gotten faster. We've got faster linear velocity because now have a look. When our wrists move that same range of motion as the first time, the bat moves a hell of a lot further. It's got a larger range of motion. So even though the angular velocity is lower, the linear velocity, so at the end of the stick, it still increases. So by having a longer lever, effectively what happens is our angular velocity, so the time that it takes for us to move our wrists in the first place, it slows down. It does come down. because the moment of inertia has increased. But it's counteracted positively that the radius is so much longer. This is significantly longer, and therefore when you multiply a longer lever, a longer radius, even by a smaller angular velocity, we get a higher linear velocity, which is at the end of the stick. So don't get confused about angular velocity versus linear velocity. We know that when moment of inertia goes up, which is this example here in the green, that our angular velocity will go down, but it's counteracted by having a longer radius of the lever, which results in a faster end speed, a faster linear velocity at the end of the stick, which is there.